So here's something worth thinking about as you settle in tonight. Right now, as you're lying there, your brain is doing something that human beings have wondered about for thousands of years. It's producing thoughts. It's generating feelings. It's aware of itself being aware. And for most of human history, nobody had any real framework for understanding how that works, or why it sometimes doesn't work. That's what psychology is. This long, winding, sometimes messy, sometimes beautiful attempt to figure out what's going on inside us. And the story of how we got from ancient guesses about the soul to modern brain scans and therapy sessions, well, it's one of the most fascinating journeys in all of human knowledge. So let's just walk through it together, nice and slow, starting from the very beginning. And I mean the very beginning, because people didn't just wake up one day in the 1800s and invent psychology. The questions that psychology tries to answer. Why do we feel what we feel? Why do we do what we do? What makes one person different from another? What happens when the mind breaks down? Those questions are as old as civilization itself. They just lived in different houses for a long time. They lived in philosophy. They lived in medicine. They lived in religion. And it took a really, really long time before anyone thought to give them a house of their own. Let's go back about 2,500 years to ancient Greece, because that's where a lot of Western thinking about the mind really starts to crystallize into something we can trace. And the person you'd want to start with is probably not who you'd expect. It's not Plato, not Aristotle. It's a physician, a man named Alcmaeon of Croton, working around 500 BCE in what's now southern Italy. Alcmaeon did something radical for his time. He dissected animals, he studied the optic nerve, and he came to a conclusion that sounds obvious to us, but was genuinely revolutionary. The brain is the organ of the mind. Thought, sensation, understanding, it all happens in the brain. Now, you might think, well, of course it does. Where else would it happen? But here's the thing. Most people in the ancient world didn't think that at all. The Egyptians, brilliant as they were at so many things, considered the brain basically useless. When they mummified a body, they'd carefully preserve the heart, the liver, the lungs, but the brain? They'd pull it out through the nose with a hook and throw it away. The heart was what mattered to them. The heart was where thought and feeling and identity lived. And that idea, the heart as the seat of the soul, was incredibly persistent. We still carry echoes of it in our language, right? We say someone has a broken heart. We say learn it by heart. We talk about heartfelt emotions. That's not just poetry. That's the residue of a very old, very deeply held belief about where the self actually resides. So Alcmaeon was pushing against a powerful current when he pointed to the brain, and his idea didn't immediately win everyone over. Even among the Greeks, there was serious disagreement. Aristotle, one of the greatest minds in human history, a man who got an astonishing number of things right, got this one wrong. Aristotle thought the heart was the center of sensation and thought. He believed the brain was basically a cooling system for the blood, like a radiator. He noticed that the brain was cool to the touch and that it seemed to have a lot of blood vessels, and he figured its job was to prevent the body from overheating. It's a reasonable guess if you don't have the tools to investigate further, but it's spectacularly wrong. And it shows you something important about the history of psychology. Even the smartest people in the world can be completely mistaken about the most basic questions when they don't have the right methods to test their ideas. But Aristotle contributed something else that matters enormously. He was obsessed with observation and classification. He wrote about memory, about dreams, about perception, about the senses, about emotions. about habit. His work, De Anima, literally, on the soul, is one of the first systematic attempts to describe the functions of the mind. And his word for soul, psyche, is the root of the word psychology itself. Psyche originally meant something like breath or life force, the animating principle that makes a living thing alive. For Aristotle, the psyche wasn't some ghostly substance floating around inside you. It was more like the organizing principle of a living body, the way a body's parts work together to produce life. That's a surprisingly modern idea in some ways, even if his specific conclusions about where it all happened were off. Now, the person who really got the brain question right, at least in the ancient world, was Hippocrates. You've heard of him. He's the one the Hippocratic Oath is named after, the father of medicine. Hippocrates, working in the 5th and 4th centuries BCE, was emphatic that the brain was the organ responsible for thought, emotion, and sensation. He wrote, and this is a remarkable passage, "Men ought to know that from the brain, and from the brain only, arise our pleasures, joys, laughter, and jests, as well as our sorrows, pains, griefs, and tears." That's from around 400 BCE, 2,400 years ago, and he nailed it. But here's what makes Hippocrates especially interesting for the story of psychology. He didn't just say, the brain matters. He tried to build a theory of personality and mental illness around physical causes. He developed the idea of the 4 humors: blood, phlegm, yellow bile, and black bile. The balance of these fluids in your body, he believed, determined your temperament. Too much blood made you sanguine, cheerful, sociable, optimistic. Too much phlegm made you phlegmatic, calm, slow, maybe a bit sluggish. Too much yellow bile made you choleric, irritable, ambitious, quick to anger. And too much black bile made you melancholic, sad, anxious, prone to deep thought. Now, the specifics are wrong. There's no black bile. Your personality isn't determined by fluid ratios, but the underlying idea that your mental state has a physical, biological basis, that mood and temperament are connected to what's happening in your body. That idea is profoundly important. It's the seed of biological psychiatry. It's the ancestor of every conversation we have today about serotonin levels and neurotransmitter imbalances. Hippocrates was groping towards something real, even if his map was way off. And there's something else worth noticing. By framing mental disturbance as a medical problem, an imbalance in the body, Hippocrates was pulling it away from the supernatural. Before him, and for a long time after him in many cultures, madness was understood as divine punishment, demonic possession, a curse from the gods. If someone was hearing voices or behaving erratically, the explanation was spiritual, and the treatment was spiritual too: prayers, rituals, exorcism. Hippocrates said no. This is a disease. It has natural causes. It can be treated with natural remedies: diet, rest, exercise, sometimes specific herbs. That shift, from the supernatural to the natural, is one of the most important moves in the entire history of psychology, and it happened remarkably early. But let's not skip over Plato, because Plato's contribution is different from Hippocrates, but equally foundational. Plato wasn't a physician, he was a philosopher, and he was interested in the structure of the soul from a completely different angle. In his dialogue, The Republic, written around 380 BCE, Plato proposed that the soul has 3 parts. There's the rational part, which seeks truth and wisdom. There's the spirited part, which seeks honor and gets angry when things are unjust. And there's the appetitive part, which seeks pleasure, food, drink, sex, comfort. For Plato, a healthy soul is one where reason governs the other two parts, the way a charioteer controls two horses. Think about that image for a second. You've got a charioteer, that's your rational mind, trying to steer two horses that want to go in different directions. One horse is noble and spirited, pulling toward glory and pride. The other is wild and unruly, pulling toward immediate gratification. The job of the charioteer is to keep them working together, moving in the right direction. If you've ever felt torn between what you know you should do and what you desperately want to do in the moment, you've lived Plato's metaphor. And if it sounds a little bit like Freud's idea, ego and superego, the impulsive unconscious, the rational self, and the moralistic conscience, well, that's not a coincidence. Freud read his Plato. These ideas have deep roots. What Plato gave us, really, was the notion of internal conflict as a fundamental feature of the human mind. You're not one unified thing. You're a collection of competing drives and impulses, and mental health depends on getting them into some kind of harmony. That's an insight that runs through virtually every school of psychology that would emerge over the next 2.5 millennia. His student Aristotle, as we mentioned, took a more empirical approach. Where Plato was abstract and idealistic, Aristotle was concrete and observational. He studied animals, categorized species, dissected specimens. He wrote about how memory works. He proposed that memories are formed through association, that one experience gets linked to another, and that recalling one can pull up the other. That's associationism, and it would become one of the most important ideas in the history of psychology, forming the backbone of learning theory all the way through to Pavlov and the behaviorists in the 20th century. But we'll get to them much later. For now, what matters is this. By the time the classical Greek period winds down, you've already got most of the big questions on the table. Is the mind in the brain or somewhere else? Is mental illness natural or supernatural? Is personality fixed or changeable? Are we rational beings or are we driven by passions we can't fully control? Do we have free will or are we determined by our nature? These aren't just ancient curiosities. These are live debates in psychology today. The Greeks didn't solve them, but they framed them with remarkable clarity. After the Greeks, the center of intellectual gravity shifts. Rome inherits Greek philosophy, but doesn't add much that's new to the psychology story. The physician Galen, working in the 2nd century CE, refines and systematizes Hippocrates' humor theory, and his version becomes the dominant medical framework for over 1,000 years. Galen is a fascinating figure, personal physician to Roman emperors, prolific writer, incredible ego. He performed public dissections and anatomical demonstrations that drew crowds. He showed that the brain controls the body by cutting specific nerves in living animals and demonstrating which functions were lost. It was brutal by modern standards, but it was also genuinely experimental. He was testing hypotheses about the nervous system in a way that wouldn't be matched for centuries. But then something happens that changes everything, and it's not a scientific discovery. It's a cultural transformation. Christianity rises, Rome falls, and Europe enters the medieval period. And for the story of psychology, this matters enormously, because the questions about the mind and soul get absorbed into theology. The soul becomes the province of the church. Understanding the mind means understanding God's creation, and the authorities on that subject are not physicians or philosophers. They're priests and monks and theologians. Now, this isn't entirely a dark age for psychological thinking. Augustine of Hippo, writing in the late 300s and early 400s CE, produced some of the most penetrating introspective writing in history. His Confessions is essentially a psychological autobiography. He examines his own memories, his desires, his will, his capacity for self-deception, with a depth and honesty that's startling even today. He wrestles with questions about habit and addiction, about why we do things we know are harmful, about the strange way memory works, storing experiences we can't always access. If you've ever tried to remember a word that's on the tip of your tongue and felt that maddening sense of almost knowing, Augustine described that experience with perfect precision 1600 years ago. But Augustine's framework is fundamentally theological. The soul's struggles are understood in terms of sin and grace, not biology or environment. And that theological framing dominates European thinking about the mind for roughly 1,000 years. Mental illness during the medieval period gets pulled back towards supernatural explanations: possession, witchcraft, divine testing. The treatments follow accordingly. Some monasteries and religious communities actually provided quite compassionate care for the mentally ill, offering shelter and routine and kindness. But others, well, the history gets darker. And the line between spiritual care and spiritual coercion could be very thin. Meanwhile, something important is happening elsewhere in the world. While Europe is deep in its medieval period, the Islamic Golden Age is flourishing, roughly from the 8th to the 14th centuries. And Islamic scholars are doing something remarkable. They're preserving and extending Greek medical and philosophical knowledge, including ideas about the mind. A Persian physician named Rhazes, working around 900 CE, wrote detailed clinical descriptions of mental illness and argued for humane treatment. Another Persian polymath, Avicenna, Ibn Sina, produced the Canon of Medicine around 1025 CE, which included sophisticated discussions of neurological and psychiatric conditions. He described conditions we'd now recognize as insomnia, mania, dementia, and hallucinations, and he proposed treatments that included music therapy, baths, and carefully structured daily routines. And here's something that doesn't get mentioned enough. The first institutions specifically dedicated to caring for the mentally ill weren't in Europe. They were in the Islamic world. Baghdad had a hospital with a ward for mental patients as early as the 8th century. Cairo, Damascus, Aleppo, these cities had facilities for the mentally ill centuries before anything comparable existed in Europe. The approach was medical, not punitive. The goal was treatment and recovery, not confinement and punishment. It's a part of the story that often gets overlooked. But it matters because it shows that the trajectory of how we understand and treat mental illness isn't a single straight line from ignorance to enlightenment. Different cultures were in different places at different times, and some of the most humane and sophisticated approaches emerged in places and periods that Western-centric histories tend to skip right over. So by the time the European Renaissance begins stirring in the 14th and 15th centuries, there's this rich, complicated, multicultural inheritance of ideas about the mind. Greek philosophy, Roman medicine, Christian theology, Islamic scholarship. All of these threads are woven together, sometimes reinforcing each other, sometimes contradicting each other. And it's in the Renaissance that something starts to shift again, because the Renaissance brings a renewed interest in the individual, in human experience, in the natural world as something worth studying on its own terms rather than purely through the lens of Scripture. And it's during this period that a very specific question starts to take on new urgency. A question that would dominate philosophical thinking about the mind for centuries, and that still, in many ways, haunts psychology today. It's the question of how the mind relates to the body. Are they the same thing? Are they different substances? If they're different, how do they interact? And the person who would frame that question most sharply, the person whose answer would shape the entire future of the field, was a French soldier and mathematician who liked to sleep in late and do his best thinking in bed, which feels appropriate for where you are right now. His name was René Descartes, and what he proposed in the early 1600s would change everything. Descartes was born in 1596 in a small town in the Loire Valley called La Haye, which was later actually renamed Descartes in his honor, which gives you a sense of just how big a deal this guy became. He lost his mother when he was just a year old, was raised largely by his grandmother, and was, by all accounts, a sickly, bookish kid. He went to a Jesuit school where he got a rigorous classical education, and the Jesuits, to their credit, let him stay in bed late in the mornings because of his fragile health, and apparently that habit stuck for life. Descartes did some of his most profound thinking while lying in bed, just letting his mind wander. There's something kind of wonderful about that. One of the most influential thinkers in the entire history of Western philosophy, doing his best work horizontal, probably half awake, staring at the ceiling. So if you're lying there right now thinking you should be doing something more productive, well, you're in good company. After school, Descartes knocked around Europe for a while, joined a couple of armies, not because he was particularly warlike, but because it was a way to travel and see the world. And it was during one of those military stints, in November of 1619, that he had a famous experience. He was stationed in Bavaria. It was winter, and he spent a day shut up in a small heated room. He called it a poêle, basically a stove-heated chamber, just thinking. And in that room, over the course of a single day, he had what he described as a series of visions or revelations about the unity of all knowledge, about how everything could be rebuilt from first principles using reason alone. It was a turning point in his life. He walked out of that room convinced that the entire edifice of human knowledge needed to be torn down and reconstructed on a foundation of absolute certainty. And this is where it gets interesting for psychology, because the tool Descartes used to find that foundation was introspection. He decided to doubt everything he'd been taught, everything his senses told him, the existence of the physical world, even mathematics. He pushed doubt as far as it could possibly go. And what he found at the bottom, the one thing he couldn't doubt, was the fact that he was doubting. He was thinking. And if he was thinking, then he must exist as a thinking thing. Cogito ergo sum. I think, therefore I am. You've heard that phrase 1,000 times, but think about what it actually means in the context of psychology. Descartes made the act of thinking itself the most fundamental certainty in the universe. He put the mind at the very center of everything. The physical world might be an illusion. Your body might be a dream. But the mind is undeniably real. Now here's the thing. Having established that the mind is this undeniable thinking substance, Descartes then had to figure out how it related to the body, which he also believed existed but which he saw as fundamentally different in nature. The mind, he said, is a non-physical substance. It thinks, it reasons, it wills, but it doesn't take up space. The body, on the other hand, is a physical substance. It's extended in space, It operates according to mechanical laws. It's basically a very sophisticated machine. This is what philosophers call substance dualism. And it's the idea that reality is made up of two fundamentally different kinds of stuff, mind stuff and body stuff. And Descartes took the machine metaphor for the body really seriously. He was fascinated by the mechanical automata of his era, those clever clockwork figures that could move and gesture and seem almost alive. He looked at animals and said, essentially, that's what they are. They're biological machines. They don't have minds, they don't have souls, they're just incredibly complex mechanisms responding to stimuli. And the human body, he argued, works the same way. Your heart pumps like a furnace, your nerves work like pipes and cables, your muscles contract through hydraulic pressure. He imagined animal spirits, these fine fluids flowing through hollow nerves, inflating muscles the way air inflates a balloon. It was wrong in the details, but the basic framework, the idea that the body operates according to mechanical, physical principles that can be studied scientifically, that was revolutionary. It gave future scientists permission to investigate the body, including the brain, as a physical system. But then you hit the problem. If the mind is non-physical and the body is physical, how do they talk to each other? When you decide to raise your arm, how does that non-physical decision cause your physical arm to move? When you stub your toe, how does that physical event create a non-physical experience of pain? This is the mind-body problem, and honestly, Descartes never solved it. He proposed that the interaction happened in the pineal gland, this tiny structure deep in the center of the brain, partly because it was one of the few brain structures that wasn't duplicated on both sides. He figured that since the mind is unified, you have one stream of consciousness, not two. It must interact with the brain through a single, central structure. It was a reasonable guess given what he knew, but it didn't actually explain the mechanism. How does a non-physical substance push around physical fluids in a physical gland? He kind of just waved his hands at that part. And this is where Descartes' legacy gets complicated, because he left psychology with an incredibly powerful framework and an incredibly difficult problem, both at the same time. The powerful framework was the idea that you could study the body, including the nervous system, including reflexes, including sensation and movement, as a purely mechanical system, using the methods of natural science. That opened the door to physiology, to neuroscience, to behavioral psychology, to everything that treats the body and brain as physical systems, subject to physical laws. But the difficult problem was this lingering dualism, this idea that consciousness, thought, subjective experience, the stuff that makes psychology, exists in some separate, non-physical realm that science can't quite reach. And in a real sense, we're still wrestling with that problem today. Every time someone asks whether a computer can truly be conscious, or what the relationship is between brain activity and subjective experience, they're asking a version of the question Descartes posed in that heated room in Bavaria 400 years ago. Now, not everyone was satisfied with Descartes' answer, obviously. Almost immediately, other philosophers started proposing alternatives. Thomas Hobbes, the English philosopher who was a contemporary of Descartes, took a much more radical position. Hobbes said there's no such thing as non-physical substance. Everything is matter in motion. The mind isn't some ghostly thing floating above the brain. It is the brain, or rather, it's what the brain does. Thinking is just a very complicated form of physical computation. Hobbes was a thoroughgoing materialist, and while his views were considered pretty scandalous at the time, he was essentially staking out the position that most neuroscientists hold today, that mental life is what physical brains produce. Then you had Baruch Spinoza, the Dutch Jewish philosopher, who proposed something different again. Spinoza said, "Mind and body aren't two separate substances. They're two aspects of one underlying substance. It's like looking at a coin from two sides. The mental and the physical are just different ways of describing the same reality." This is called dual aspect theory, or sometimes neutral monism, and it's actually a surprisingly modern-sounding idea. Some contemporary philosophers of mind have come back to something very much like Spinoza's position. And then there was Gottfried Wilhelm Leibniz, the German polymath who co-invented calculus and who proposed yet another solution. Leibniz argued that mind and body don't actually interact at all. They just run in perfect parallel, like two clocks synchronized by God at the moment of creation. Your decision to raise your arm and your arm actually rising happen simultaneously, but one doesn't cause the other. God set it all up in advance. This is called pre-established harmony, and it sounds bizarre, but it was a serious attempt to solve the interaction problem without violating the laws of physics. The point of all these competing theories isn't that you need to remember each one. It's that the mind-body problem Descartes crystallized was so fundamental, so difficult, that it consumed some of the greatest minds in Europe for generations. And each proposed solution carried implications for what psychology could be. If Hobbes was right and everything is physical, then psychology should ultimately be reducible to physics and biology. If Descartes was right and the mind is non-physical, then psychology needs its own methods, its own tools, because you can't put consciousness under a microscope. These aren't just abstract philosophical puzzles. They're the foundational questions that determine what kind of science psychology can be. But while the philosophers were arguing about the nature of mind, something else was happening in the 17th and 18th centuries that would prove just as important for psychology's future. The empiricists were building a theory of how the mind actually acquires knowledge, and their answer was going to lay the groundwork for everything from behavioral psychology to modern cognitive science. The key figure here is John Locke, an English physician and philosopher, who published his essay concerning human understanding in 1689, and who proposed one of the most influential metaphors in the history of ideas. Locke said the mind at birth is a tabula rasa, a blank slate. There are no innate ideas, no built-in knowledge, no pre-installed concepts of God or mathematics or morality. Everything you know, everything you think, every concept in your head got there through experience, through your senses. You see, you hear, you touch, you taste, you smell, and from those raw sensations, your mind builds up simple ideas. And then from those simple ideas, through processes of combination and abstraction and comparison, you build up complex ideas. The entire architecture of human thought, in Locke's view, is constructed from the bottom up, brick by brick, out of sensory experience. Now think about what that means for psychology. If Locke is right, then the mind isn't some mysterious preloaded thing. It's a product of its environment, its experiences, its history. You want to understand why someone thinks the way they do? Look at what they've experienced. You want to change how someone thinks? Change their experiences. This is the philosophical seed that would eventually grow into behaviorism, into learning theory, into the entire tradition of psychology that focuses on how the environment shapes the person. And Locke's emphasis on experience also implied something methodological. If knowledge comes from observation, then the study of the mind should also be based on observation, not just armchair speculation. Locke's ideas were picked up and pushed further by subsequent empiricists. George Berkeley, the Irish philosopher, took empiricism in a startling direction by arguing that physical objects only exist insofar as they're perceived. Esse est percipi. To be is to be perceived. And then David Hume, the brilliant Scottish philosopher, writing in the mid-1700s, took the whole empiricist project to its logical extreme and arrived at conclusions that were genuinely unsettling. Hume argued that we never actually perceive causation. We just perceive one event following another, and our minds develop a habit of expecting the sequence to continue. The self, he said, is nothing but a bundle of perceptions, one flowing into the next, with no underlying substance holding them together. There is no little observer sitting inside your head watching the show. There's just the show. And here's what's remarkable. Hume was essentially describing something that Buddhist philosophers had been saying for over 2,000 years. This idea that the self is an illusion, a construction, a narrative we tell ourselves. But Hume arrived at it through pure philosophical reasoning within the Western empiricist tradition, and the implications for psychology were enormous. Because if there's no fixed self, if the mind is just a stream of experiences and associations, then psychology isn't studying a thing, it's studying a process, a flow. And that idea that the mind is better understood as a verb than a noun, as something that happens rather than something that is, would echo through the centuries all the way to William James and the stream of consciousness, all the way to modern process-based therapies and dynamic systems theory. But we're getting ahead of ourselves, because before psychology could become a science, before anyone could set up a laboratory and start measuring mental processes, something else had to happen. The body itself, particularly the nervous system, had to be understood as a physical system that could be studied experimentally. And that story takes us into the 18th and 19th centuries, into anatomy theaters and physiology labs, into a series of discoveries about nerves and brains and reflexes that would finally lay the groundwork for everything that followed. And it starts, fittingly enough, with a question that sounds almost childishly simple. How do nerves actually work? What are they doing when you touch something hot and your hand jerks away? What's traveling along those fibers, and how fast does it move? For a long time, the best answer anyone had was still basically Descartes' answer: animal spirits, some kind of fluid flowing through hollow tubes. And honestly, that wasn't a terrible guess given what people could observe at the time. But by the mid-1700s, researchers were starting to poke at this idea, quite literally, and finding that the reality was far more interesting. One of the key figures here is a Swiss physician and polymath named Albrecht von Haller. Now, Haller was one of those people who just seemed to do everything. He wrote poetry, he wrote novels, he compiled massive encyclopedias of botany, and he performed what might be the most systematic set of physiological experiments anyone had attempted up to that point. Working in Göttingen in the 1750s, Haller did something that was both brilliantly methodical and, honestly, pretty hard to think about. He systematically stimulated different tissues in living animals to figure out which parts of the body could feel and which parts could move. He drew a crucial distinction between what he called irritability and sensibility. Irritability was the capacity of muscle fibers to contract when stimulated. You poke a muscle, it twitches, even if it's been cut away from the nerve. Sensibility was the capacity to feel, to transmit sensation, and that required intact nerves running back to the brain or spinal cord. Now, this might sound obvious to us, But think about what Haller was really establishing here. He was showing that the nervous system has a specific, identifiable function. It carries sensation. And that this function is different from what muscles do on their own. He was pulling apart the machinery, figuring out which component does what. And that's the essential move that had to happen before psychology could become experimental. You have to understand the hardware before you can start asking questions about the software. Around the same time and into the early 1800s, another debate was heating up, one that would prove enormously consequential. It's called the Bell-Magendie debate, and it centers on a discovery so fundamental that it's hard to overstate its importance. Charles Bell, a Scottish anatomist working in London, and François Magendie, a French physiologist working in Paris, both arrived at essentially the same finding, though they argued bitterly about who got there first. What they discovered was that the spinal nerves have two separate roots, a dorsal root and a ventral root, and these roots do different things. The dorsal roots carry sensory information into the spinal cord. The ventral roots carry motor commands out to the muscles. Sensation in, movement out. Two separate channels. Bell published a privately circulated pamphlet about this around 1811, but his evidence was somewhat ambiguous and his reasoning partly theoretical. Magendie, in 1822, did the definitive experiments, cutting the roots in living animals and observing what happened. Cut the dorsal root, and the animal loses sensation in that area, but can still move. Cut the ventral root, and sensation remains, but movement is lost. Clean, clear, undeniable. And here's why this matters so much for the story of psychology. This discovery established that the nervous system isn't just one undifferentiated mass of tissue doing vague things. It has specific pathways for specific functions. Information flows in particular directions along particular routes. The nervous system has an architecture, a wiring diagram, and you can map it. That idea that mental functions might be localized, that different parts of the nervous system do different jobs, would become one of the most productive and also most controversial ideas in the entire history of brain science. Which brings us, almost inevitably, to one of the most colorful and strange episodes in this whole story, the rise and fall of phrenology. And I want to spend a little time on this, because phrenology is one of those things that people tend to dismiss as pure quackery, and in many ways it was, but the kernel of the idea behind it was actually genuinely important, and the story of how it went wrong tells you something deep about the relationship between good ideas and bad methods. Franz Joseph Gall was a Viennese physician born in 1758 who became obsessed with a deceptively simple observation. He noticed, or believed he noticed, that people with particularly strong mental traits, good memory, musical talent, aggressiveness, seemed to have distinctive shapes to their skulls. From this, he developed an elaborate theory. The brain, Gall argued, is the organ of the mind. So far so good. Alcmaeon would have agreed. But then Gall went further. He proposed that the brain is not a single uniform organ, but a collection of separate organs, each responsible for a different mental faculty. There was an organ for benevolence, one for combativeness, one for philoprogenitiveness, which is just a wonderful word meaning love of offspring, one for secretiveness, and so on. He identified 27 of these faculties initially, and his followers would eventually expand the list. Here's the thing, though. Gall's core insight that different parts of the brain do different things was actually correct. That's the principle of cortical localization, and it's one of the foundational ideas of modern neuroscience. Where Gall went catastrophically wrong was in his method. He assumed that if a particular brain region was well developed, it would be physically larger, and that this enlargement would push out the skull above it, creating a bump you could feel with your fingers. So you could read someone's personality by feeling the bumps on their head. And that, well, that's where it falls apart. The shape of your skull doesn't reliably reflect the shape of the brain underneath. The whole measurement system was based on a false premise. Gall's student, Johann Spurzheim, took the ideas even further, popularized them, gave them the name phrenology, and turned the whole thing into a cultural phenomenon. By the 1830s and 1840s, phrenology was everywhere, in parlors, in lecture halls, in hiring decisions. People would have their heads read the way they might check their horoscope today. Queen Victoria had her children's heads examined by a phrenologist. It was a sensation, but serious scientists were already pushing back. The most devastating critique came from Pierre Fleuron, a French physiologist who took a very different approach to the question of brain localization. Instead of feeling skulls, Fleuron actually removed parts of animal brains, primarily pigeons and rabbits, and observed what happened. His method was called ablation, and his results seemed to contradict Gall completely. When Flourens removed the cerebral hemispheres, animals lost all perception and judgment. When he removed the cerebellum, they lost coordination. But within the cerebral hemispheres themselves, Flourens couldn't find the kind of neat localization Gall predicted. Damage to one area of the cortex seemed to produce much the same general impairment as damage to another area. Flourens concluded that the cerebral cortex functions as a whole. He called this the principle of equipotentiality, and that Gall's map of separate organs was fiction. Now, here's what's fascinating. Flourens was wrong too, or at least partly wrong. The cortex is not equipotential. Different regions really do specialize in different functions, as later researchers would dramatically demonstrate. But Flourens was working with small-brained animals and relatively crude techniques, and the specialization in a pigeon brain is much less pronounced than in a human brain. So both Gall and Flourens had part of the truth, and both were wrong in important ways, and the real answer would take decades more to emerge. The breakthrough that really settled the localization question, at least for language, came in the 1860s, and it came from a case that's become one of the most famous in the history of neuroscience. Paul Broca was a French physician and anatomist, and in 1861 he encountered a patient at the Bicêtre Hospital in Paris who had been there for over 20 years. The patient's name was Louis Victor Le Borgne, but everyone called him Tan because that was essentially the only syllable he could produce. He could understand language perfectly well. He could follow instructions. His intelligence seemed intact, but when he tried to speak, all that came out was tan, tan, tan. Occasionally, he could produce an oath or a short phrase, but sustained speech was impossible. When Le Borgne died, Broca performed an autopsy and found a lesion, an area of damage, in the left frontal lobe, specifically in a region of the inferior frontal gyrus. Broca went on to examine several more patients with similar speech difficulties, and in case after case, the damage was in the same area, and it was almost always on the left side. This was enormous. It meant that a specific mental function, the ability to produce speech, was localized in a specific region of the brain, and moreover, it was lateralized, concentrated on one side rather than the other. The region became known as Broca's area, and the condition became known as Broca's aphasia. About a decade later, in 1874, A German physician named Karl Wernicke described a different kind of language problem. His patients could speak fluently. They produced grammatically complex sentences with normal rhythm and intonation, but what they said made no sense. They strung words together in ways that sounded like language but carried no meaning, and they couldn't understand what was said to them. Wernicke found that these patients had damage in a different region, further back in the left hemisphere, in the superior temporal gyrus. This became Wernicke's area, and the condition became Wernicke's aphasia. Think about what this means for a second. You have two different brain regions, both involved in language, but doing completely different jobs. One handles the production of speech, the motor planning, the coordination of mouth and tongue and larynx to form words. The other handles comprehension, the ability to extract meaning from the sounds you hear. Damage one, and you can understand but can't speak. Damage the other, and you can speak but can't understand. The architecture of the mind was being revealed, one clinical case at a time. And Wernicke went even further. He predicted that there should be a bundle of nerve fibers connecting his area to Broca's area, and that if this bundle were damaged, you'd get a third kind of aphasia. A patient who could speak and could understand but couldn't repeat what was said to them, because the connection between comprehension and production was severed. This is called conduction aphasia, and it was later confirmed. Wernicke was building a model of the brain as a network, not just a collection of isolated modules, but an interconnected system where information flows between specialized regions along specific pathways. This was the nervous system revealing itself as something mappable, something with a logic you could trace. And all of this, the localization debates, the aphasia cases, the careful clinical anatomical correlations, was happening in the same decades that another, parallel revolution was unfolding. Because while some researchers were asking where in the brain mental functions lived, others were asking a different question entirely, a question that might sound even simpler, but turned out to be just as profound. They were asking, how fast does a thought travel? And the person who figured out how to answer that question was a man named Hermann von Helmholtz. And his story is one of those stories that makes you realize how tangled together all the sciences really were in the 19th century. Helmholtz wasn't just a physiologist. He wasn't just a physicist. He was both, and a mathematician, and an inventor, and honestly, one of those figures who makes you wonder how one human brain could hold so many projects at once. Born in 1821 in Potsdam, just outside Berlin, he grew up in a family that didn't have a lot of money. His father was a gymnasium teacher. That's a secondary school in the German system. And young Hermann wanted to study physics, but his family couldn't afford university tuition. So he made a practical choice. He enrolled in a military medical institute in Berlin, which was free, on the condition that he'd serve as an army surgeon for several years after graduating. And that detour through medicine turned out to be one of those happy accidents that changes the course of science, because it meant Helmholtz got rigorous training in anatomy and physiology alongside his natural gift for physics and mathematics. He was the right person, with the right combination of skills, standing at exactly the right intersection of disciplines. Now, here's the context you need to appreciate what he did. Before Helmholtz, the prevailing assumption, and this was held by serious, respected scientists, was that nerve impulses traveled either instantaneously or so fast that they could never be measured. Johannes Müller, who was actually one of Helmholtz's own teachers and one of the most important physiologists of the era, had flatly stated that the speed of nerve transmission was too fast to measure. Müller thought it might approach the speed of light. And there was a philosophical reason people were comfortable with this idea. If the mind was something special, something elevated, maybe even something divine, then it made a kind of intuitive sense that its signals would be immeasurably swift. The idea that a thought might take time to travel, that there would be a measurable delay between a stimulus touching your finger and your brain registering it, felt almost reductive to some people. It seemed to drag the mind down into the realm of ordinary physical processes. Helmholtz didn't care about any of that. In 1850, he did something beautifully simple. He took a frog's leg, a dissected frog nerve muscle preparation, the kind of thing physiologists had been working with since Galvani's day, and he stimulated the nerve at two different points, one close to the muscle and one farther away. Then he measured the difference in time it took the muscle to twitch in each case, and the answer was stunning. The nerve impulse traveled at roughly 25 to 30 meters per second. Not the speed of light, not instantaneous, about the speed of a good fastball. Think about what that means. A signal traveling from your toe to your brain takes a measurable fraction of a second. Your nervous system isn't some ethereal, instantaneous communication network. It's a physical system with physical limitations, and those limitations can be clocked with a stopwatch. Well, with a very precise instrument called a galvanometer. But you get the idea. This was a bombshell, and Helmholtz knew it. He wrote to a friend that he'd expected the speed to be much higher, and even he was surprised at how slow it was. But the measurement was solid, and it changed everything about how scientists thought about the relationship between mind and body. If nerve signals take time, then mental processes take time. And if mental processes take time, then you can measure them. You can study them experimentally. You can put numbers on them. This was one of those moments where a single experiment cracks open an entire field of inquiry. Helmholtz had shown that the tools of physics could reach into the territory that had belonged to philosophy and pull out hard data. And he didn't stop there. Helmholtz went on to do extraordinary work on the physiology of perception, specifically vision and hearing. His book on physiological optics, published in the 1850s and 1860s, was a masterwork. He figured out how the eye focuses, proposed the young Helmholtz trichromatic theory of color vision, the idea that we have three types of color receptors in the retina, sensitive to different wavelengths, and that all the colors we perceive are mixtures of these three signals. This is still basically correct, by the way. Every color screen you've ever looked at, every phone, every television, uses red, green, and blue pixels to create the full spectrum of color. And that works because your eyes actually do have three types of cone cells tuned roughly to those wavelengths. Helmholtz figured this out in the 1850s. He also invented the ophthalmoscope, the instrument doctors still use to look into your eye. He was that kind of person, the kind who doesn't just theorize but builds the tools. His work on hearing was equally remarkable. He proposed a resonance theory of pitch perception, the idea that the cochlea, the spiral-shaped structure in your inner ear, contains fibers of different lengths that resonate at different frequencies, like the strings of a piano. A high-pitched sound sets the short fibers vibrating. A low-pitched sound sets the long ones going. This turned out to be not quite right in its details. The mechanism is more complex than simple resonance, but the core insight that the cochlea performs a kind of frequency analysis and that different parts of it respond to different pitches was absolutely on the right track. Helmholtz was mapping the engineering of perception, showing how the raw physical world of light waves and sound waves gets translated into the subjective experience of seeing and hearing through specific, identifiable biological mechanisms. But here's what's really important for our story. All of this work, the nerve speed measurements, the studies of vision and hearing, was creating a foundation. It was showing that mental life could be studied with the methods of natural science. And that foundation was exactly what a younger generation of researchers would build on. Because if you can measure how fast a nerve impulse travels, maybe you can measure how long it takes a person to react to a stimulus. And if you can measure reaction time, maybe you can start to measure the duration of mental processes themselves. Maybe you can put the mind on the laboratory bench, and that's exactly what happened in Leipzig, Germany in 1879 when a former student of Helmholtz's named Wilhelm Wundt did something that sounds almost anticlimactic when you describe it, but was genuinely revolutionary. He opened a laboratory. That's it. He established a formal, dedicated laboratory for the experimental study of psychology at the University of Leipzig. It wasn't the first time anyone had done psychological experiments. Helmholtz had been doing them. Gustav Fechner had been doing them. Others had been doing them in scattered ways for years. But Wundt created an institutional home for the discipline. He gave it a physical space, a research program, students, a journal to publish in. He said, in effect, psychology is its own science now, not a branch of philosophy, not a sideline of physiology, its own thing, with its own methods and its own questions. Wundt was a meticulous, systematic, almost obsessively productive man. He published an astonishing amount. Estimates vary, but something on the order of 50,000 pages over his career. He trained dozens of doctoral students who went on to establish psychology laboratories across Europe and North America. If you want to pick a single moment when psychology became a formal academic discipline, Wundt's Leipzig laboratory in 1879 is the conventional choice, and it's a pretty good one. Now, what did they actually do in that laboratory? Wundt's primary method was something he called experimental introspection. The idea was to present carefully controlled stimuli, lights, sounds, weights, pressures, and have trained observers report their conscious experiences in precise, standardized terms. Not just, I see a light, but a detailed, structured account of the qualities of the experience, its intensity, its duration, its character. Wundt believed that consciousness could be broken down into its basic elements, the way a chemist breaks compounds into elements. He was looking for the atoms of mental life. This approach came to be called structuralism, and its goal was to map the structure of conscious experience through rigorous, controlled introspection. And there's something elegant about it, right? It's a direct extension of the empiricist tradition we talked about earlier. Locke's simple ideas combining into complex ones, Hume's impressions and ideas. Wundt was trying to do experimentally what the British empiricists had done philosophically, identify the building blocks of the mind. But he was doing it in a laboratory, with instruments and controlled conditions, and multiple observers checking each other's reports. The problem, and this became apparent fairly quickly, was that introspection is tricky. Different laboratories, using slightly different methods, got different results. Wundt's lab in Leipzig would report one set of basic mental elements. Edward Titchener, an Englishman who had studied with Wundt and then moved to Cornell University in the United States, would report a somewhat different set. Titchener was actually more extreme than Wundt in some ways. He pushed structuralism further, insisting that all conscious experience could be reduced to sensations, images, and affections, and he trained his observers to avoid what he called the stimulus error, which was describing the object rather than the experience. Don't say, I see a red apple. Say, I experience a patch of redness of such and such saturation and brightness. It was rigorous in its way, but it was also fragile because it depended entirely on the subjective reports of trained observers, and there was no independent way to verify those reports. This vulnerability would eventually be structuralism's undoing. But before that happened, something else was stirring. A completely different way of thinking about what psychology should be studying. Because while Wundt and Titchener were trying to identify the elements of consciousness, a group of American thinkers were asking a very different question. They weren't interested in what the mind is made of. They were interested in what the mind is for. And the person who crystallized this shift was a man with one of the most fascinating minds in American intellectual history, William James, a philosopher, psychologist, physician, and writer who could make even the most abstract ideas feel alive and urgent on the page. James had been thinking about consciousness not as a structure to be dissected, but as a process, a flowing, ever-changing stream. In fact, he coined a phrase for it that you've almost certainly heard before. He called it the stream of consciousness. And his vision of what psychology could be was about to collide with Wundt's vision in a way that would reshape the entire field. And reshape it did. Because William James didn't just disagree with structuralism. He found it almost comically beside the point. In his masterwork, The Principles of Psychology, published in 1890, James laid out a vision of psychology that was sweeping, vivid, and relentlessly practical. The book took him 12 years to write, and it ran to nearly 1,400 pages across 2 volumes. James himself jokingly called it a loathsome, distended, tumefied, bloated, dropsical mass, which gives you a sense of his personality right there. But that massive, sprawling book became one of the most influential texts in the history of psychology, and for a simple reason, James wrote about the mind the way people actually experience it. Where Wundt and Titchener wanted to freeze consciousness in place and catalog its elements like a chemist listing compounds, James insisted that consciousness doesn't work that way. It doesn't sit still. It flows. It moves. It shifts from one thing to the next in a continuous, unbroken current. And the moment you try to grab a piece of it and hold it up for inspection, you've already changed it. You've killed the very thing you're trying to study. He compared it to trying to catch a snowflake. The warmth of your hand melts it the instant you close your fingers. That's why he called it a stream. Not a chain of links, not a mosaic of tiles, but a stream, always moving, always blending one moment into the next. And here's where the functionalist question really bites. James wasn't interested in breaking consciousness into its smallest parts. He wanted to know what consciousness does. What purpose does it serve? Why do we have it at all? And this question came directly out of an intellectual revolution that was sweeping through biology at the same time. Darwin's theory of evolution by natural selection. Think about what Darwin's framework implies. If a trait exists in an organism, it's because that trait helped the organism's ancestors survive and reproduce. Resistance to a particular disease, the shape of a beak, the ability to see in color, these things aren't accidents. They're adaptations. And James looked at consciousness and asked the same question. If the mind does things, if it perceives, remembers, reasons, feels emotion, then those capacities must serve some function. They must help us navigate the world, solve problems, avoid dangers, seize opportunities. Psychology, in James's view, should be studying those functions. Not what the mind is made of, but what it's for. This was a profoundly American way of thinking, and that's not a coincidence. The philosophical tradition that James drew on was pragmatism, developed by his friend and colleague Charles Sanders Peirce, and later expanded by John Dewey. Pragmatism held that the meaning of an idea lies in its practical consequences. An idea is true insofar as it works, insofar as it helps you deal with reality. And functionalism in psychology was pragmatism applied to the mind. Don't ask what consciousness is in the abstract. Ask what it does in practice. Ask how it helps a living creature adapt to its environment. Now, James himself was a complicated figure, and his life story matters for understanding why he thought the way he did. He was born in 1842 into a wealthy, intellectually eccentric New York family. His father, Henry James Sr., was a Swedenborgian theologian who dragged the family back and forth across the Atlantic, enrolling the children in schools in Geneva, Paris, London, Bonn. William attended something like a dozen schools before he was 18. His brother was Henry James, the novelist. The family dinner table was apparently a non-stop philosophical debate society. William started out studying painting, then switched to chemistry at Harvard, then switched to medical school, then suffered a devastating period of depression in his late 20s, a crisis so severe that he later described it as a kind of existential paralysis, a feeling that free will was an illusion and that nothing he did could possibly matter. He pulled himself out of it, in part, by choosing to believe in free will as a pragmatic act, by deciding that the belief itself was useful, that it enabled him to function, and that this was sufficient justification for holding it. You can hear the seeds of his entire philosophy in that personal crisis. James joined the Harvard faculty in 1872, initially teaching physiology, then psychology, then philosophy. He set up a small demonstration laboratory for psychology around 1875, which some historians argue was actually the first psychology laboratory in the world, predating Wundt's by a few years. Though Wundt's was more systematic and more clearly dedicated to original research, so the priority question is genuinely debated. But the point is that James was there at the very beginning, helping to define what this new science would look like. And what he thought it should look like was broad. Incredibly broad. The principles of psychology covers perception, habit, attention, memory, reasoning, emotion, the self, will, and more. James wrote about each of these not as abstract structures, but as living processes that do things for the organism. Take his theory of habit, for instance. James argued that habits are essentially neural pathways that become more efficient with repetition. The more you do something, the easier it becomes, because the nervous system physically changes to accommodate the repeated action. And this matters, James said, because habits are what allow us to function without having to consciously think about every little thing. You don't think about how to tie your shoes anymore. You don't deliberate about which foot to put forward when you walk. Those actions have been delegated to habit, freeing up your conscious attention for higher-level problems. Habit, in other words, is an adaptation. It serves a function. Or take his theory of emotion, which is genuinely one of the most counterintuitive ideas in all of psychology. Common sense tells you that you see a bear, you feel afraid, and then you run. The emotion causes the physical response. James flipped this completely around. He argued that you see the bear, you run, and then you feel afraid, that the emotion is actually your brain's perception of the bodily changes that are already happening. Your heart is racing, your muscles are tense, your breathing is shallow, and the feeling of fear is simply your awareness of those physical states. A Danish physiologist named Carl Lang proposed essentially the same idea independently around the same time, so it became known as the James Lang theory of emotion. And here's the thing, it sounds bizarre at first, but there's a kernel of real insight in it. Modern research has shown that bodily states genuinely do influence emotional experience. People who receive Botox injections that prevent them from frowning report feeling slightly less sad when viewing upsetting images. People who are told to smile, even artificially, sometimes report feeling marginally happier. The relationship between body and emotion runs in both directions, which is at least partly what James was getting at. But anyway, the larger point is that functionalism opened up psychology in ways that structuralism never could. If you're interested in what mental processes do, rather than what they're made of, then suddenly the range of things you can study expands enormously. You can study children and how their mental abilities develop. You can study animals and compare their capacities to ours. You can study people with mental illness and ask how their psychological functions have gone awry. You can study individual differences, why some people are better at certain tasks than others. Structuralism was narrow by design. Functionalism was expansive by philosophy. And this expansion had real-world consequences. One of the most important was the rise of mental testing. If people differ in their psychological capacities, can you measure those differences? Can you quantify intelligence? This question would become one of the most consequential and most controversial in the entire history of psychology. The story starts in England with a man named Francis Galton, who was, incidentally, Charles Darwin's half-cousin. Galton was obsessed with measurement. He measured everything: the weather, the efficacy of prayer, the beauty of women in different British cities, which he mapped by secretly counting attractive and unattractive faces as he walked down the street. He was brilliant and eccentric, and it must be said, deeply problematic, because his interest in human differences led him to found the eugenics movement, which would go on to cause enormous harm in the 20th century. But Galton's contribution to psychology specifically was the idea that mental ability could be measured through simple sensory and motor tests: reaction time, grip strength, sensory acuity. He set up an anthropometric laboratory at the 1884 International Health Exhibition in London, where visitors could pay threepence to have their various capacities measured. Thousands of people went through it. Galton believed that people with sharper senses and faster reactions would also be more intelligent, because he assumed that all information enters the mind through the senses. So better senses should mean a better mind. He was wrong about that, as it turned out. A student of Wundt's named James McKean Cattell brought Galton's testing approach to the United States and administered batteries of these sensory motor tests to Columbia University students. But when another psychologist, Clark Whistler, correlated the test results with the students' academic grades in 1901, he found essentially no relationship. Fast reaction time didn't predict good grades. Grip strength didn't predict good grades. The Galton-Cattell approach to measuring intelligence was a dead end, but the idea of mental testing itself was very much alive. It just needed a different approach. And that different approach came from France, from a psychologist named Alfred Binet, who was asked by the French government in 1904 to solve a very practical problem. France had recently passed laws requiring all children to attend school, and teachers were struggling with students who couldn't keep up. The government needed a way to identify children who needed extra help. Not a theoretical framework, not a philosophical argument, but a working tool. Binet, working with his colleague Theodore Simon, took a completely different approach from Galton. Instead of measuring simple sensory abilities, he tested complex mental tasks, reasoning, comprehension, judgment, memory. He arranged the tasks in order of difficulty and determined what a typical child of each age could do. If a 7-year-old could solve the problems that most 7-year-olds could solve, that child had a mental age of 7. If a 7-year-old could only solve problems typical of 5-year-olds, that child had a mental age of 5. The gap between mental age and chronological age indicated how much help the child might need. The Binet-Simon scale, first published in 1905 and revised in 1908 and 1911, was a genuinely practical tool, and it worked remarkably well for its intended purpose. But here's what's crucial. Binet himself was very cautious about what his test meant. He did not believe it measured some fixed, innate quantity called intelligence. He explicitly warned against using the scores to label children permanently. He believed intelligence was malleable, that education could improve it, and that his test was a diagnostic tool, not a destiny stamp. That caution would be almost entirely ignored when the test crossed the Atlantic. An American psychologist at Stanford University named Louis Terman adapted the Binet-Simon scale for American use, publishing it in 1916 as the Stanford Binet Intelligence Scale. Terman introduced the concept of the intelligence quotient, the IQ, calculated by dividing mental age by chronological age and multiplying by 100. And Terman did not share Binet's caution. He believed intelligence was largely hereditary, largely fixed, and he was enthusiastic about using IQ scores to sort people into educational tracks, into occupational categories, into judgments about their worth and potential. The testing movement exploded during World War I, when the U.S. Army needed to rapidly sort nearly 2 million recruits. Robert Yerkes, then president of the American Psychological Association, led the effort to develop the Army Alpha and Army Beta tests. Alpha for literate recruits, Beta for illiterate ones, and suddenly intelligence testing was operating at an industrial scale, with enormous social consequences that are still being debated today. Because once you start sorting people by a number, once you attach a single score to a human being and call it their intelligence, you've created something incredibly powerful and incredibly dangerous at the same time. And the thing is, the Army testing program didn't just affect the military. It changed American society. After the war ended, those tests, and the mindset behind them, spilled out into schools, into immigration policy, into courtrooms, into the national conversation about who was smart and who wasn't, who deserved opportunity and who didn't. The results from the Army tests were published by Yerkes in a massive 1921 report, and they showed, among other things, that recruits from certain immigrant groups, particularly those from Southern and Eastern Europe, scored lower on average than recruits from Northern European backgrounds. Now, there were obvious reasons for this that had nothing to do with innate intelligence. Many of these men had arrived in the United States recently, spoke little English, had limited formal education, and were unfamiliar with American cultural references that were baked right into the test questions. The Army Alpha test asked things that assumed a certain kind of cultural knowledge, but those nuances were largely swept aside. The results were seized upon by eugenicists, people who believed that the human race could and should be improved through selective breeding, as scientific proof that certain racial and ethnic groups were inherently less intelligent. And this wasn't a fringe movement. Eugenics had powerful supporters in American academia, in politics, in philanthropy. The testing data became ammunition for the Immigration Restriction Act of 1924, which dramatically reduced immigration from Southern and Eastern Europe and effectively barred immigration from Asia. A psychological test designed to sort Army recruits helped reshape who was allowed to become an American. Think about that for a second. A tool that started as Benet's humble diagnostic instrument for identifying school children who needed extra help in Paris had, within 2 decades, become a weapon of social policy on the other side of the world. And Binet himself had died in 1911, before any of this happened. He never saw what became of his creation. There's something deeply sad about that. A careful, thoughtful scientist whose explicit warnings were stripped away as his invention was repurposed for exactly the kind of deterministic labeling he feared. Now, this doesn't mean intelligence testing was entirely without value. The tests did reveal real differences in cognitive performance, and they were genuinely useful in educational settings when used the way Binet intended, as diagnostic tools to identify where someone needed support. The problem was never the measurement itself. The problem was the interpretation, the assumption that the score reflected something fixed and biological rather than something shaped by education, environment, language, nutrition, opportunity. That debate, nature versus nurture in intelligence, would run through the entire 20th century, and it's still running today. We'll come back to it. But let's shift gears a bit, because while the testing movement was reshaping how psychology engaged with the practical world, something else was happening that would reshape the theoretical foundations of the field entirely. And it starts with a man you've almost certainly heard of, even if you've never studied psychology for a single day in your life. Sigmund Freud. Here's the thing about Freud. He's simultaneously the most famous psychologist who ever lived and one of the most controversial. Depending on who you ask, he was either a genius who unlocked the hidden depths of the human mind, or a brilliant storyteller who built an elaborate theory on shaky evidence and personal intuition. The truth, as usual, is somewhere in between, and it's more interesting than either extreme. Freud was born in 1856 in Freiburg, Moravia, that's in what's now the Czech Republic, and grew up in Vienna. He trained as a physician, specializing in neurology, and early in his career, he did legitimate, respected work on aphasia and cerebral palsy. He was a serious scientist, but he became increasingly interested in patients whose symptoms didn't seem to have any clear physical cause. Paralysis without nerve damage, blindness without eye problems, pain without injury. These cases were often lumped under the diagnosis of hysteria, a catch-all term that had been used for centuries, usually applied to women, usually with vague and unhelpful explanations attached. In the mid-1880s, Freud traveled to Paris to study with Jean-Martin Charcot, a famous French neurologist at the Salpêtrière Hospital who was using hypnosis to study hysteria. Charcot demonstrated something remarkable. He could use hypnotic suggestion to produce hysterical symptoms in patients, and he could use it to remove them. This meant the symptoms were somehow psychological in origin, not physical. The body was responding to something happening in the mind. That idea hit Freud hard. It suggested there were mental processes operating beneath conscious awareness that could produce real, tangible, physical effects. Back in Vienna, Freud began collaborating with an older physician named Joseph Breuer, who had been treating a patient known in the literature as Anna O. Her real name was Bertha Pappenheim, and she would later become a prominent social worker and feminist activist, which is its own fascinating story. Anna O. suffered from a constellation of symptoms: partial paralysis, visual disturbances, difficulty speaking, and Brewer discovered that when she talked about her symptoms under hypnosis, tracing them back to specific emotional experiences, the symptoms often improved or disappeared. She herself called the process the talking cure, and that phrase stuck. Freud and Brewer published their findings together in 1895 in a book called Studies on Hysteria, but they soon parted ways because Freud was pushing the theory in directions Brewer wasn't comfortable with. Specifically, Freud was becoming convinced that the hidden emotional experiences driving these symptoms were almost always sexual in nature. This would become one of the most contentious aspects of Freud's work, this insistence on sexuality as the primary engine of psychological life. Over the next decade, Freud developed what he called psychoanalysis, both a theory of the mind and a method of treatment. And here's where it gets really interesting from a structural standpoint, because what Freud proposed was genuinely radical. He argued that the mind is mostly unconscious. The thoughts and feelings you're aware of, your conscious experience, are just the surface. Beneath that lies a vast reservoir of desires, memories, conflicts, and impulses that you don't have direct access to, but that profoundly shape your behavior, your emotions, your relationships, your dreams, your slips of the tongue, everything. He eventually developed a structural model of the mind with three components: the id, the ego, and the superego. The id is the primitive, unconscious part that operates on the pleasure principle, demanding immediate gratification of basic drives. The superego is the internalized voice of social and moral standards, the conscience, and the ego is the mediator, the part that navigates between the id's demands, the superego's prohibitions, and the constraints of external reality. Think of it like a negotiation that's happening constantly beneath the surface of your awareness, competing forces pulling you in different directions, and the ego trying to broker some kind of workable compromise. Now, whether you find this model convincing or not, and many modern psychologists don't, at least not in its original form, you have to appreciate what Freud was doing. He was saying that human beings are not the rational, transparent to themselves creatures that Enlightenment philosophy had imagined. You don't fully know why you do what you do. Your reasons are often hidden from you. Your conscious explanations for your behavior are often rationalizations, stories you tell yourself after the fact to make sense of actions driven by forces you can't see. That idea, that we are strangers to ourselves in fundamental ways, was genuinely unsettling, and it changed the way Western culture thinks about the mind. It seeped into literature, into art, into film, into how we talk about relationships and motivation in childhood. Even people who reject Freud's specific theories live in a world shaped by his central insight. But here's where the criticism comes in, and it's serious. Freud built his theories primarily on case studies, individual patients he treated in his private practice in Vienna. These were mostly upper-middle-class women in a very specific cultural context. The sample was tiny and unrepresentative. His methods of interpretation were subjective and often unfalsifiable, meaning there was no way to prove them wrong. If a patient agreed with Freud's interpretation, that confirmed the theory. If the patient disagreed, that was resistance, which also confirmed the theory. Karl Popper, the philosopher of science, would later use psychoanalysis as his prime example of a theory that fails the test of falsifiability. If nothing could possibly count as evidence against your theory, then your theory isn't really scientific. And yet, Freud's influence was enormous. psychoanalysis became the dominant force in psychiatry and clinical psychology for the first half of the 20th century, especially in the United States. Analysts trained for years, patients lay on couches, and free associated for sessions that stretched over months and years, and the whole enterprise became deeply embedded in medical culture and popular culture alike. Freud also attracted brilliant followers who eventually became brilliant dissenters. Carl Jung, originally one of Freud's closest collaborators, broke with him around 1912 over theoretical disagreements. Jung wanted to expand the concept of the unconscious beyond personal experience to include what he called the collective unconscious, a shared reservoir of archetypes and symbols common to all humanity. Alfred Adler split even earlier, rejecting Freud's emphasis on sexuality and proposing instead that the primary human motivation was the striving for superiority, the drive to overcome feelings of inferiority and achieve competence and mastery. These breakups were bitter and personal, as intellectual breakups often are when the stakes feel existential. Freud could be dogmatic and punishing toward anyone who deviated from his framework, and the psychoanalytic movement sometimes resembled a religious sect more than a scientific community. But while psychoanalysis was dominating the clinical world, a completely different revolution was brewing in academic psychology, one that would reject not just Freud's theories, but the entire enterprise of studying the mind at all. And the person who lit that particular fuse was an American psychologist named John B. Watson, who in 1913 published a paper that essentially declared war on everything psychology had been doing since Wundt opened his laboratory in Leipzig. Watson's argument was blunt and provocative. Psychology, he said, should stop trying to study consciousness. Consciousness can't be observed, can't be measured, can't be verified. Introspection is unreliable. The unconscious is untestable. All of it, structuralism, functionalism, psychoanalysis, was built on quicksand. The only thing psychology can legitimately study, Watson argued, is behavior. Observable, measurable, public behavior. Not what people think or feel, but what they actually do. He called this approach behaviorism, and it would dominate American psychology for the next half-century, reshaping the field so thoroughly that by the 1950s, talking about the mind in a psychology department was almost professionally dangerous. It was that total a takeover. Now, Watson himself is a fascinating character, and his story is worth slowing down for, because it tells you something about how ideas gain power, and how the people behind them are always more complicated than the ideas themselves. John Broadus Watson was born in 1878 in a small town near Greenville, South Carolina. His childhood was rough. His father drank heavily and eventually left the family when Watson was 13. His mother was deeply religious, and Watson would later rebel against that religiosity with a kind of fierce, almost allergic secularism. He was, by his own admission, a difficult kid, got arrested twice as a teenager, was a mediocre student, and seemed headed nowhere in particular. But he talked his way into Furman University at 16, and something clicked. He ended up at the University of Chicago for graduate work, studying under some of the leading functionalists of the day, and he earned his PhD in 1903 with a dissertation on rat behavior, specifically, how rats learn to navigate mazes. And here's the thing about that dissertation. Watson found that he could study learning perfectly well without ever asking the rat what it was thinking. The rat's behavior told you everything you needed to know. It turned a corner, it hit a dead end, it tried a different path, it eventually found the food. You could time it, count errors, track improvement across trials. It was clean, it was objective, and it was replicable. And Watson started to wonder, why couldn't we study humans the same way? That question simmered for about a decade before Watson put it into print. His 1913 paper, usually called Psychology as the Behaviorist Views It, is sometimes referred to as the Behaviorist Manifesto, and it reads like one. It's combative, it's confident, and it draws a hard line. Psychology, Watson declared, is a purely objective experimental branch of natural science. Its theoretical goal is the prediction and control of behavior. That word control is important. It tells you Watson wasn't just interested in understanding what organisms do. He wanted to know how to make them do specific things. And the tool for that, he believed, was conditioning. Watson didn't invent conditioning. That credit goes to Ivan Pavlov, the Russian physiologist who had been working with dogs in St. Petersburg since the 1890s. Pavlov's original research was on digestion. He was studying how dogs salivated in response to food, and he'd actually won the Nobel Prize in Physiology or Medicine in 1904 for that digestive work. But Pavlov noticed something strange. After a while, his dogs started salivating, not just when food appeared, but when they heard the footsteps of the lab assistant who usually brought the food. The dogs had learned to associate a neutral stimulus, footsteps, or later, a metronome or a bell, with the arrival of food. Pavlov called this a conditioned reflex. The dog wasn't born salivating at the sound of a bell. It had learned to, through repeated pairing of bell and food. And when Pavlov started systematically studying this process, ringing the bell, presenting food, measuring saliva, varying the timing, introducing new stimuli, he mapped out a set of principles that were remarkably orderly. You could condition a response. You could extinguish it by stopping the food. You could see it spontaneously recover after a rest period. You could observe the dog generalizing its response to similar sounds. It was learning, stripped down to its mechanical essentials. Watson seized on Pavlov's work and made it the foundation of behaviorism. If you could condition a dog to salivate at a bell, Watson reasoned, then maybe all learning, all of it, in every organism including humans, was just conditioning. We come into the world as blank slates, and the environment writes on us through associations. Watson made this argument in its most extreme and famous form in 1930, when he wrote that famous passage, you've probably heard some version of it, where he claimed that if you gave him a dozen healthy infants and his own specified world to bring them up in, he could guarantee to take anyone at random and train that child to become any type of specialist he might select. Doctor, lawyer, artist, merchant, even beggar and thief, regardless of the child's talents, tendencies, abilities, or the race of its ancestors. It's a breathtaking claim, and Watson himself acknowledged in the very next sentence that he was going beyond his facts. But the rhetorical power of that statement captured something essential about the behaviorist worldview, the idea that we are made, not born, that the environment is everything. Watson's most notorious experiment came in 1920, and it's one of those stories that makes you wince a little. Working with a graduate student named Rosalie Rayner at Johns Hopkins University, Watson conducted what's now called the Little Albert experiment. They took a 9-month-old infant, identified in the literature only as Albert B., and systematically conditioned him to fear a white rat. Albert had initially shown no fear of the rat at all, happily reaching for it. But Watson and Rayner began pairing the presentation of the rat with a sudden loud noise. They struck a steel bar with a hammer right behind the baby's head. After several pairings, Albert began to cry and withdraw whenever the rat appeared, even without the noise. And the fear generalized. Albert showed distress toward other furry objects, a rabbit, a dog, even a Santa Claus mask with a white beard. Watson had demonstrated, or at least believed he had demonstrated, that emotional responses like fear could be created through simple conditioning. The experiment raises all kinds of ethical red flags by modern standards. The child was never deconditioned. Watson and René didn't undo the fear they'd created. Albert was removed from the hospital where the study took place before they could attempt it, or so the story goes. For decades, nobody knew what happened to little Albert. Researchers eventually tracked down a likely candidate, a boy named Douglas Merritt, who turned out to have had significant neurological problems and who died at age 6 of hydrocephalus. That identification is still debated, and another researcher has proposed a different child named William Albert Barger, who lived a long life and apparently had no particular aversion to animals. The uncertainty itself tells you something about how casually early psychology sometimes treated its subjects. But here's what's really interesting about Watson's career. It ended abruptly, and not because of little Albert. In 1920, Watson was fired from Johns Hopkins because of a scandalous affair with Rosalie René, who was not only his graduate student, but also came from a prominent Baltimore family. Watson's wife discovered love letters, a divorce followed, and Johns Hopkins let him go. Watson married René, but he never held an academic position again. He went into advertising and was spectacularly successful at it, applying behavioral principles to sell coffee and baby powder and cigarettes. He became a vice president at J. Walter Thompson, one of the biggest ad agencies in the world. There's something almost poetic about the founder of behaviorism spending his later career figuring out how to condition consumers to buy things. Watson's exile from academia didn't slow behaviorism down, though. If anything, it freed the movement to evolve beyond Watson's relatively simple stimulus-response framework. And the person who took behaviorism to its most sophisticated and influential form was B.F. Skinner, who is arguably the most important psychologist of the 20th century, depending on who you ask and how you're measuring importance. Burrhus Frederick Skinner, and yes, his first name really was Burrhus, was born in 1904 in Susquehanna, Pennsylvania, a small railroad town. He originally wanted to be a writer. He studied English at Hamilton College, and after graduating, he spent what he later called his dark year, trying to write fiction and failing. He read some of Watson's work, discovered Pavlov, and decided that psychology was where the real action was. He enrolled at Harvard in 1928 and never looked back. Skinner's key innovation was distinguishing between two types of conditioning. Pavlov's classical conditioning, bell, food, salivation, was about reflexive responses, things the organism does automatically. But Skinner was more interested in what he called operant conditioning, which deals with voluntary behaviors. The core idea is simple and powerful. Organisms tend to repeat behaviors that are followed by pleasant consequences, and they tend to stop behaviors that are followed by unpleasant ones. Reinforcement increases behavior. Punishment decreases it. And the specific patterns of reinforcement, what Skinner called schedules of reinforcement, produce remarkably predictable patterns of behavior. Skinner studied this with extraordinary precision using a device he invented called the operant conditioning chamber, though everyone else called it the Skinner box. It was a small enclosed space, usually containing a lever or a button that an animal, typically a rat or a pigeon, could press or peck. When the animal performed the target behavior, it received a food pellet or some other reward. Skinner could vary the schedule, reward every single press or every fifth press or on a random interval. And he found that each schedule produced a distinctive, predictable pattern of responding. Variable ratio schedules, where the reward comes after an unpredictable number of responses, produce the highest and most persistent rates of behavior. And if that sounds familiar, it should. It's exactly the principle behind slot machines, behind the pull-to-refresh mechanism on your phone, behind every app that gives you notifications at irregular intervals to keep you checking. Skinner mapped the architecture of habit decades before Silicon Valley weaponized it. Skinner was also a tireless inventor and a bold, sometimes controversial thinker. He built a temperature-controlled crib for his infant daughter called the baby tender, essentially a climate-controlled box with a window, and the press misreported it as raising a baby in a Skinner box, which horrified the public. He designed a guidance system during World War II that used trained pigeons to peck at a target on a screen to steer a missile. Project Pigeon, it was called. And it actually worked in testing, though the military never deployed it because, well, it was pigeons steering missiles. And in 1948, he published a utopian novel called Walden 2, which imagined a community designed entirely on behavioral principles, where reinforcement schedules replaced laws and social norms, and everyone was happy because the environment was engineered to make them happy. The book was polarizing. Some readers found it inspiring. Others found it terrifying. A vision of humanity reduced to trained pigeons in a very large, very comfortable box. And that tension between the undeniable power of behavioral principles and the deeply uncomfortable implications of applying them to human life would haunt behaviorism for its entire reign. Because by the 1950s, behaviorism was the dominant paradigm in American psychology. It controlled the journals, the departments, the funding. If you wanted a career in academic psychology, you studied behavior. You ran rats. You avoided words like mind and consciousness and thought, as if they were professional poison. The inner life of the organism was a black box, and you didn't open black boxes. You just measured what went in and what came out. But here's the thing about black boxes. Eventually, someone gets curious enough to pry one open. And by the late 1950s, cracks were starting to appear in the behaviorist edifice, cracks that would widen into a full-scale revolution. The first serious blow came from an unlikely direction: linguistics. In 1959, a young MIT linguist named Noam Chomsky published a devastating review of Skinner's 1957 book, Verbal Behavior, in which Skinner had tried to explain language entirely through reinforcement principles. Chomsky argued with surgical precision that this simply could not work. Children don't just repeat sentences they've been reinforced for saying. They generate entirely novel sentences they've never heard before, following grammatical rules no one explicitly taught them. A 3-year-old who says, "I goed to the store," has never been reinforced for that particular utterance. The child is applying a rule. Past tense means add ed and overgeneralizing it. That's not conditioning. That's something happening inside the black box. That's cognition. Around the same time, a British psychologist named Donald Broadbent was studying attention, specifically how people manage to focus on one voice in a noisy room, the cocktail party problem. His 1958 book, Perception and Communication, proposed that the mind contains an internal filter that selects which information gets processed and which gets ignored. This was an explicitly mentalistic model. It talked about information flow inside the organism, about processing stages, about internal representations. And it worked. It predicted experimental results that behaviorism simply couldn't account for. And then there were the computers. The development of digital computers in the 1940s and 1950s gave psychologists something they'd never had before: a metaphor for the mind that was both mechanical and mentalistic. A computer takes in information, processes it through a series of internal operations, stores it in memory, and produces output. You could talk about what was happening inside the machine without being mystical about it. The mind could be studied as an information processing system, and suddenly the black box wasn't just openable, it was the whole point. The black box wasn't just openable, it was practically begging to be opened. And that changes everything. See, what happened in the late 1950s and into the 1960s wasn't just a correction to behaviorism. It was a full-blown revolution in how psychologists thought about thinking itself. And like most revolutions, it didn't have a single leader or a single moment. It was more like a dozen different streams all converging into one river at the same time. You had Chomsky showing that language required internal rules. You had Broadbent showing that attention required internal filters. You had computer scientists building machines that processed information through internal operations. And you had a growing number of psychologists who were just tired of pretending that the most interesting questions about human beings were off limits. The term that eventually stuck was cognitive psychology, and if you had to pick one book that crystallized the whole movement, it would probably be Ulrich Neisser's 1967 book, simply titled Cognitive Psychology. Neisser was a German-born American psychologist working at Cornell, and what he did in that book was pull together all these scattered threads: perception, attention, memory, language, thinking, and present them as parts of a single coherent framework. The mind, Neisser argued, is an information processing system. It takes in sensory data, transforms it, stores it, retrieves it, and uses it to guide behavior. And every one of those steps can be studied scientifically, with rigorous experiments, without apologizing for the fact that you're talking about what happens inside someone's head. Now, here's what's really clever about the cognitive revolution. It didn't throw out everything the behaviorists had built. The experimental rigor, the insistence on controlled studies, the careful measurement of behavior, all of that stayed. What changed was the scope of what you were allowed to study. Behaviorists said, we can only study inputs and outputs, stimuli and responses. Cognitive psychologists said, we can study inputs and outputs, and we can also make inferences about what happens in between, as long as those inferences are testable. It was an expansion, not a demolition. And the timing was perfect, because right around this period, some genuinely beautiful experimental work started coming out of memory research. Think about a psychologist named George Miller. In 1956, Miller published one of the most cited papers in the history of psychology. It had a wonderfully playful title: The Magical Number 7, Plus or Minus 2. What Miller showed was that human short-term memory has a limited capacity. You can hold roughly 7 items in mind at once, give or take a couple. Phone numbers, by the way, are 7 digits long for exactly this reason. But here's the interesting part. Miller also showed that you can get around this limitation through what he called chunking. If I give you the letters F, B, I, C, I, A, I, R, S, that's 9 items, and it's hard to hold them all. But if you recognize the chunks, FBI, CIA, IRS, suddenly it's only 3 items, and it's easy. Your mind is reorganizing the information, grouping it, compressing it. That's not a stimulus-response association. That's active mental processing. That's cognition happening in real time. And then there was the work on different types of memory altogether. By the late 1960s, researchers like Richard Atkinson and Richard Schifrin proposed what became known as the modal model of memory. The idea that memory isn't one thing, but at least three. Sensory memory, which holds raw perceptual information for just a fraction of a second. Short-term memory, which holds a small amount of information for maybe 20 or 30 seconds. And long-term memory, which can store vast amounts of information more or less permanently. Information flows from one store to the next, and at each stage it can be lost or transformed. It's a beautiful model, and it maps surprisingly well onto how computers work. Input buffer, working memory, hard drive. That metaphor again. But here's where it gets really interesting, because as cognitive psychology matured through the 1970s and 1980s, researchers started discovering that the mind is far stranger and more complicated than any simple computer metaphor suggests. Take the work of Daniel Kahneman and Amos Tversky. These two psychologists, working together primarily in the 1970s, showed that human thinking is riddled with systematic biases and shortcuts, what they called heuristics. People don't process information like rational computers. They take mental shortcuts that are usually pretty good, but sometimes lead to predictable errors. Here's a classic example. Kahneman and Tversky asked people, are there more English words that start with the letter K, or more words that have K as their third letter? Most people confidently say there are more words starting with K. But actually, there are roughly 3 times as many words with K as the third letter. Think ask, acknowledge, lake. The reason people get it wrong is something called the availability heuristic. It's easier to think of words that start with K, because that's how we organize words in our minds, so we judge them as more common. Our cognitive system isn't broken. It's using a shortcut that works well most of the time, but misfires in this particular case. Think about what that means. The mind isn't just processing information, it's processing it in specific, quirky, sometimes irrational ways that tell you something deep about its architecture. Kahneman would eventually win the Nobel Prize in Economics in 2002 for this work. A psychologist winning the Nobel in Economics, which tells you something about how far psychology's reach had extended. And while cognitive psychology was mapping the mind's information processing quirks, another revolution was happening simultaneously, one that would eventually merge with it. This was the neuroscience revolution, the idea that you could study not just the mind as an abstract information processor, but the actual physical brain that implements it. Now, we talked earlier about Broca and Wernicke back in the 1860s and 1870s, finding specific brain regions linked to specific language functions. That work had continued quietly through the 20th century, but it was limited by the tools available. You could study brain damage in patients. You could do some electrical stimulation during surgery, but you couldn't really watch a healthy brain in action. That changed dramatically in the 1990s with the development of functional magnetic resonance imaging, fMRI. For the first time, researchers could watch blood flow patterns in a living, working brain while a person performed a cognitive task. You could ask someone to read a sentence, or look at a face, or make a moral judgment, and actually see which brain regions became more active. It was like finally being able to open the hood of a car while it was running. The 1990s were officially declared the decade of the brain by President George H.W. Bush, and the field of cognitive neuroscience, the marriage of cognitive psychology and brain science, absolutely exploded. Now, I should be honest here. Brain imaging is powerful, but it's also been overhyped. Early fMRI studies sometimes fell into a trap that critics called neophrenology, just pointing to a brain region lighting up and saying, "That's where love lives," or "That's the fear center." The reality is far more complex. Most cognitive functions involve networks of brain regions working together, not single spots. And the fMRI signal is indirect. It measures blood oxygenation, not neural activity directly, and it's sluggish, capturing changes over seconds when neurons fire in milliseconds. But even with those limitations, neuroimaging has transformed psychology. It's given us a way to connect mental processes to physical mechanisms, to bridge that gap between mind and brain that Descartes worried about 400 years ago. And that brings us to something worth sitting with for a moment, because as psychology moved into the 21st century, it faced a reckoning that was, in its own way, as important as any theoretical revolution. Starting around 2011, a social psychologist named Daryl Bem published a paper claiming to show evidence for precognition, that people could be influenced by events that hadn't happened yet. The paper was methodologically conventional by the standards of the field. It used the same statistical methods, the same experimental designs that psychologists had been using for decades, and yet its conclusions were, to put it gently, implausible. This sparked something remarkable. Researchers started asking, if our standard methods can produce evidence for psychic powers, maybe there's something wrong with our standard methods. What followed was the replication crisis, a period of intense self-examination in which psychologists tried to reproduce classic findings and discovered that many of them couldn't be replicated. A massive 2015 project led by Brian Nosek attempted to replicate 100 published psychology studies. Only about 36% produced results consistent with the originals. 36%. That's sobering. The causes were multiple and interconnected. Small sample sizes. Flexible data analysis, what critics called p-hacking, where researchers could unconsciously tweak their analyses until they got a statistically significant result. Publication bias, meaning journals preferred to publish exciting positive findings and ignored null results, so the published literature was systematically skewed. And pressure, the relentless academic pressure to publish novel, surprising findings or perish. But here's the thing, and this is important. The replication crisis, painful as it was also a sign of health. Psychology was doing something that most fields rarely do, turning its tools on itself, rigorously questioning its own foundations, and making concrete changes. Pre-registration of studies became more common, meaning researchers had to specify their hypotheses and methods before collecting data, so they couldn't change the rules after the fact. Larger sample sizes became the norm. Open data practices spread. The field didn't collapse. It grew up. And that brings us, gently, to where psychology stands now, in this still unfolding present moment. The field today is almost unrecognizably vast compared to what Wundt started in that single room in Leipzig in 1879. There are cognitive psychologists studying how you form memories and make decisions. There are clinical psychologists developing evidence-based therapies. Cognitive behavioral therapy, or CBT, which directly applies cognitive principles to treat depression and anxiety, is one of the most well-validated treatments in all of medicine. There are developmental psychologists mapping how children's minds unfold from infancy. There are social psychologists studying how groups influence individuals, how prejudice forms, and how it might be reduced. There are neuroscientists tracing the exact circuits that underlie consciousness itself, though that particular puzzle, what philosophers call the hard problem, remains as deep and mysterious as ever. And there's something poetic about that. if you think about it. We started this whole journey thousands of years ago, with Aristotle sitting in Athens, wondering what the soul was made of, whether it lived in the heart or the head. We followed that question through medieval monasteries and Islamic libraries, through Descartes sitting by his fire wondering how he could be certain of anything, through the careful measurements of Weber and Fechner, through Wundt's metronomes and Titchener's trained introspectors, through James's restless brilliance and Freud's shadowy unconscious, through Watson's rats and Skinner's pigeons and the sterile elegance of the stimulus response chain. We watched the black box get sealed shut and then pried back open. We watched the mind become an information processor, and then something stranger and more beautiful than any computer. And after all of that, after all those centuries of asking and arguing and building instruments and running experiments and getting things spectacularly wrong and then slowly, painfully getting them a little more right, we're still asking essentially the same question. What is this thing, this experience of being a conscious mind in a physical world? How does 3 pounds of wet tissue generate the feeling of being you? We don't have the full answer yet. We may not have it for a very long time. But the asking, the careful, patient, humble asking, that's the whole story. That's what all those people were doing, every single one of them, from Aristotle to the graduate student running an fMRI scan tomorrow morning. They were all just trying to understand the one instrument we can never put down, the one lens we can never look behind, the mind that's doing the looking. And you know, there's something deeply comforting about that. Right now, as you're lying here, your brain is doing 1,000 things you'll never be aware of, consolidating memories from today, regulating your breathing, drifting through the edges of consciousness towards sleep. All those processes that so many brilliant, stubborn, curious people spent their lives trying to understand, they're happening in you, right now, effortlessly. You don't have to think about any of it. Your mind knows what to do. It's been doing it for a very long time. So let it do its work. Let the questions rest for tonight. They'll still be there in the morning, patient and fascinating as ever, waiting for whoever wants to pick them up next. For now, though, just this. Just the quiet. Just the slow, easy drift toward wherever your mind wants to take you.